Hello, good morning, afternoon, evening, depending on when you're looking at this talk. I am Elena Queirolo. I am now a postdoc at the Technical University of Munich, and I've been collaborating with Professor Kuhn on neural networks and how to apply computer validation techniques to neural networks. I would like here to present our first results on this topic. And I hope you'll be finding that interesting because I'm quite excited about it myself. So at first, let's look at a one-step RNN in which at each layer of our RNN, we are only doing the predictor step, not the correction step. So by this, I mean that every layer of the RNN that we are going to indicate by T, because we want to go towards the formulation of ODs, our behavior at layer T plus 1 is equal to the behavior at times T plus some nonlinearity applied to a linear transformation of the previous layer, plus some new information given by some data that just arrived, and a bias. So in here we have W, that is the matrix of weights, so how much each term of the previous layer influences the new layer. V, dt are the new data that we are introducing into the system at every single step size, and V is their impact on the new behavior, and B is a vector of biases that we can introduce for extra flexibility. The interesting part in here is this sigma, that is the nonlinear transformation between this linear term and the new behavior of the layer. And if we assume this nonlinearity sigma to be in some senses small, so that can be written as like epsilon times some other nonlinearity sigma tilde, then we can rewrite this with this form that you might notice it being something as numerical mathematicians that we're relatively familiar with. This is a forward Euler's method. So we can look at this simplified RNN as each layer being an application of the forward Euler method to the previous step. In some senses, we want to look at this as if to say that underneath this RNN formulation, there is an ODE formulation, a continuous, smooth definition of an ODE system, of a dynamical behavior that is behind what the RNN is literally computing. We call this new formulation neural flow, and I find this extremely important because it allows us to go from a computer science environment to a mathematical environment in which we have techniques that have been developed over hundreds of years, quite literally, that allows us to determine the dynamics behind this ODE that we're looking at. So we are dropping the computer science background to be able to use in full the techniques we know best. We also want to specifically look at a setup of RNNs without chaos. So if the matrix W is chosen with all generality, we might have the situation in which the behavior of our layers tends to be chaotic with respect to the input. And that's definitely not something that is interesting in practicalities. So we want to avoid chaotic behavior, and to do that, one possibility is to set some conditions on sigma and W. We want sigma to be the hyperbolic tangent plus an epsilon term, and W to be roughly anti-symmetric. Actually, we want W to be exactly anti-symmetric based on the matrix W hat, plus a diagonal term that allows us to shift things. Because things are usually not exact, we allow for W to also have a perturbation matrix. So W will be computed of like an anti-symmetric matrix, a diagonal shift, and a perturbation of the Wolf setting. In this case, we'll look at epsilon and gamma as hyperparameters. We are not specifically interested in epsilon, that being only the precision of the forward Euler method we're using, but we will be focusing most in gamma, since that enters into our weight matrix and can have significant impact on the dynamics we're looking at. So if we're either looking at the ODE setup or at the RNN setup, we're going to be dropping the bias vector and the new data input. So we're looking at a simplified version in which no extra information gets fed into the system at every step size. And we're only looking at the behavior from layer to layer that we have. Going to the ODE setup, then we just have a hyperbolic tangent depending on a linear transformation of x. Here we explicitly write gamma, and we keep this dependency on gamma when we want to look at changes on the dynamics depending on this parameter. Whatever the gamma is, the unique equilibrium of this problem is at x equal to 0, assuming w is non-singular. Because the unique equilibrium is known analytically, we can also compute the Jacobian at the equilibrium analytically, and that turns out to be exactly W gamma. Most of the rest of the techniques that we're looking at will not depend on this specific structure, but this specific structure allows us to understand a bit better how the expected behavior of the system is going to be. That means that, in particular, to study the bifurcations that the unique equilibrium is undergoing, we are allowed to study directly W gamma in the specific setup. One of the bifurcations I'm interested in looking at in this setup is the Hopf bifurcation. And the Hopf bifurcation, new periodic orbits are generated from the equilibrium point. So following the equilibrium point with respect to the parameter gamma, we have that there is a shift in stability of the equilibrium, and a periodic orbit gets generated that orbits around the equilibrium, at least for small enough parameter gamma. This Hopf bifurcation happens when a pair of eigenvalues crosses the imaginary axis. For the Hopf bifurcation to be non-generic, we also want this crossing of the eigenvalues to be with non-zero speed with respect to the parameter. So we really want a gamma to push the eigenvalues through the imaginary axis with non-zero velocity and not a tangency. Since we are allowed to look at the Jacobian of the system explicitly, we can have some intuition about what sorts of behaviors this W gamma can have. If W would be exactly antisymmetric with no diagonal shift and no perturbation, then the eigenvalues would be imaginary, purely imaginary. So we would have no Hopf bifurcation because it would be constantly on the imaginary axis. With the diagonal shift that we have introduced with gamma, that means that we're having these eigenvalues having real part equal to gamma. So they are all crossing the imaginary axis at the same time. So the eigenvalues would be complex for all values of gamma different than 0. This is why, from a mathematical perspective, the introduction of the perturbation term is very important, because it allows us to scatter the points at which these eigenvalues cross the imaginary axis. With no perturbation, we would have a very degenerate Hopf bifurcation in which we would have many imaginary eigenvalues crossing. With the introduction of the perturbation, on one side we'll lose these analytical statements, on the other we're able to retrieve non-degenerate Hopf bifurcations. So the validated results in this case are this combination of an analytical intuition and computations that allow us to consider the specific case for any given perturbation of the system. So we are able to give proof of bifurcation even in cases in which W is not exactly antisymmetric with a diagonal. Let me give some time to look at the setup for the zero finding problem. I assume we're all fairly familiar with validated techniques. So once we have a full handle of the zero finding problem, we're able to set up validation techniques explicitly, such as the application of radii polynomials or any other validation technique you might be interested in. So our first goal is to set up the half bifurcation problem as a zero finding problem such that we're able to use our techniques. So we're looking at a generic ODE depending on a parameter, and we wonder how to set up a system that allows us to have half bifurcations. At the moment, I'm not looking at degenerate or non-degenerate half bifurcations, just the setup in which we're restricting the eigenvalues to be imaginary. So at first, we want to solve for the equilibrium. So we want f of x and gamma to be equal to 0. And then we want the Jacobian to have imaginary eigenvalues. If we straightforwardly write the eigenvalue problem of the f, we'll have the fact that the Jacobian is real while the eigenvector is complex and the eigenvalue is purely imaginary. So we would have to have some numerical problems in setting up the system very precisely. What we do instead is writing the eigenvector as a sum of a real part and an imaginary part, and the eigenvalue as a purely imaginary component. Then we can rewrite our eigenvalue problem as a two-component, the solution of the real part of the eigenvalue problem and the solution of the imaginary part of the eigenvalue problem. So now we have added two sets of equations to our problem. They're both on the zero finding setup. We also have to add a scaling of the eigenvectors. We need two new equations to scale for VR and VI. And now we have a square system that is finite dimensional for looking for our eigenvalues and eigenvectors. Now that we have a zero finding problem, we can use radii polynomial approach to prove the existence of the imaginary eigenvalues. And since we have a direct handle on the bounds for the solution of our equilibrium problem, we can use those bounds to have a bound on the Jacobian, so knowing exactly how wrong the Jacobian is, and we can use techniques to prove that the eigenvalues and eigenvectors are indeed close to what we're saying they should be. So we have a two-part setup. One is we find the solution to this problem, we prove its results, and the second one, for proving the non-degeneracy of the problem, we also want to check that no other eigenvalue is crossing the imaginary axis at the same time. We do that with a quite brute force approach, just checking that all other eigenvalues at a given gamma are not on the imaginary axis. And then we can use the results to explicitly compute the Lyapunov exponent, the Lyapunov coefficient, the first Lyapunov coefficient. That gives us that the results, that the half bifurcation is non-degenerate. So we have a full handle on non-degeneracy of every half bifurcation we can find. As a result, given any W hat and P square matrices of the same size, we can usually find all the gammas such that W gamma has imaginary eigenvalues, so that our ODE is undergoing a potentially degenerate half bifurcation. And then we can check the half bifurcation for non-degeneracy. We're usually able to prove non-degeneracy, and when we can't prove non-degeneracy, we're usually able to find that it is indeed degenerate for some reason. Usually because P is not large enough to allow for all the half bifurcations to be separate. In this picture here, we have a two-dimensional example in which we could create random matrices W hat and P. We could find the half bifurcations, and we could numerically follow the periodic orbit out of the half bifurcation. And we can validate the result with the combination of radial polynomial and Lyapunov coefficient computation. In the same ways as the two-dimensional example, we can scale up very easily. Since all our computations in this case are all linear computations, or very close to the linear computations, we're able to look at very large problems. And here we have a 20-dimensional example in which we have set up W hat and P to be random matrices. We could validate the 10 half bifurcations of this 20-dimensional example, and then we could numerically follow all of the branches. Since all Lyapunov coefficients that we have found were positive, we can prove that all the periodic orbits that we have found, we're not giving a statement of all possible periodic orbits, only the ones that we have found, are all unstable. So here is a 6-dimensional example in which we have found all the half bifurcations, so 3 half bifurcations, and we have set ourselves close to one half bifurcation, and we have looked for the periodic orbit. Since it is unstable, after some time, our numerical method becomes unstable and we drift away from the periodic orbit. So we have transient dynamics. Just as a counterpoint to see how different the dynamics is, the second picture is a forward integration started at a random point. So not close to the half bifurcation, not close to the periodic orbit. And we see how qualitatively the two behaviors are significantly different. As I was saying before, all our techniques are very computationally light, so it's possible to look at very large examples. Here, I could look at a 400 dimensions example. As before, I found all the 200 half bifurcations. I could validate all of them, and here I could look at one specific gamma close to half bifurcation and look for the transit dynamics close to that. Again, we have on the left the transient dynamics. Plotted for a very short time, we already see that the second oscillation is a bit larger than the previous one. And on the right, a completely random initial point, just computed forward in time. I only plotted 6 coordinates of our periodic orbit, or our orbit in general, to allow to still see something. Otherwise, if we were plotting all the 400, that would be complicated. I am honestly not sure why there are so many oscillations around the periodic orbit on the left side. It is my understanding that it's probably given by the numerical method used by MATLAB in the integration. These are not validated results. The only validation we have done are on the bifurcations themselves. I hope you found this presentation interesting, and thanks for your attention.